Okay, so it's time for a very rich but technically complicated mathematical physics problem. In this video, I'm going to show you how to use the Gupta-Bleuler Quantization prescription to quantize the free electromagnetic field. Now, there's a lot more sophisticated concepts involved here. It may seem like, why would you want to do this if you've got the Coulomb prescription, which is so much less complicated? It's much more straightforward. It seems so easy, and there are a few different reasons why. One, when you go to quantize more sophisticated theories, it turns out that the Gupta-Bleuler type approach, or at least an approach that uses a gauge-fixing Lagrangian, is way easier to use. Also, because of the loss of manifest Lorentz covariance in the Coulomb gauge prescription, the calculations tend to be longer and more difficult. So this actually makes practical calculations easier once you have the theory quantized, even if the quantization itself is a bit more complicated. This prescription is used so much all over high energy physics, it's important to get used to it, it's important to learn it, and with a theory as simple as free electromagnetism, it's really a good exercise to begin that process. This is kind of a long video, it's kind of an intricate one. The math is not easy. I explain all of it in complete detail. I show you all the calculations, so you shouldn't get stuck. Hopefully you don't, because everything is given, but still it's quite a lot to take in. This is a bit of a step up from the Coulomb gauge calculation. And so now the following math section contains all of the details of this quantization procedure. This calculation is done in natural units. Also, the mostly minuses metric signature is used for the Minkowski metric in these calculations. The Lagrangian density of the free electromagnetic field is simply this, the Maxwell-Lagrangian density without an interaction term, where this is the formula for the field strength tensor in terms of the 4-vector potential. Because A mu is a real vector field and there is no mass term, we are dealing with a massless spin-1 chargeless field theory. Now remember the gauge invariance of this theory. This gauge invariance will be important later. We will now try and quantize the theory as is. It turns out that very quickly we will run into problems. The first step is, of course, to calculate the conjugate fields. We see the problem immediately, pi 0 equals 0. Because pi 0 equals 0, the canonical equal time commutation relations cannot possibly be satisfied here, because they would demand that the commutator of phi with 0 is some non-zero number, which is impossible. It turns out that one can solve this problem by breaking the gauge. There are many specific prescriptions for fixing this problem, because there are many different ways of breaking the gauge. In this case, we will use a gauge-fixing Lagrangian density in a program called Gupta-Bleuler Quantization. One is free to add terms to the Lagrangian density of the quantum field theory as long as those terms can be made to vanish by the imposition of some valid gauge condition. Gauge-breaking terms that cannot be made to vanish via the application of some valid gauge condition are not allowed because they change the value of the S matrix. Terms that can be made to vanish by the imposition of some valid gauge condition leave the S matrix unaffected because it is gauge invariant, and there exists some valid gauge condition that eliminates the extra term. Of course, because this theory is non-interacting, the S matrices are kinda trivial, but still, all I said about it is true. This is the most common way to break the gauge in quantum field theory because it is convenient and one can make the gauge breaking terms proportional to arbitrary parameters that can be set to different values to yield different gauges. For example, in quantum electrodynamics, the Lorentz gauge condition allows the following exceedingly common gauge-fixing Lagrangian to be added on without affecting the S matrix. This one. So the standard gauge-fixed Maxwell-Lagrangian density is just this. Given that the gauge-fixing term vanishes in the Lorentz gauge, we are guaranteed that quantizing this theory will lead to all the same physics that the Maxwell theory did. As it turns out, there will be unphysical states in the Fock space that we need to eliminate with a physical state condition, but that is not novel physics that results from the gauge-fixing Lagrangian. All this gauge condition means is that the gauge-fixing Lagrangian won't introduce any novel physics. It doesn't mean that we will eliminate any unphysical physics that comes from treating the normal Maxwell Lagrangian. If there's anything unphysical that we need to deal with in the Maxwell Lagrangian, then adding this term specifically won't affect anything, meaning that will still be there and we'll still need to deal with it. In this case specifically, the 4-vector potential has a temporal or scalar component and a longitudinal component, which of course correspond to unphysical photon polarizations. This is the ultimate origin of those unphysical states. The physical state condition that we will need to impose to eliminate those unphysical states is actually inspired by the Lorentz gauge condition. With this Lagrangian established, we can proceed to some more manipulations and ultimately quantization. Now we can rewrite the Lagrangian in a useful way. First, let's plug in the field strength tensors here. We get that. Integrating by parts and ignoring the boundary terms because the fields are taken to vanish at infinity allows us to go from this to this, which can then be rewritten like this. So then we have this form of the action here where we get this operator. This operator right here is actually quite interesting. If the gauge fixing term in the Lagrangian we got this from hadn't been there, then this would actually have come out to be a projection operator. An operator specifically that projects out all of the modes that would normally be affected by the gauge transformation. But because this would be a gauge invariant theory without that gauge fixing Lagrangian density, in that case we know those gauge transformations couldn't affect the theory. So the fact that this would come out a projection operator, if we hadn't added that gauge fixing Lagrangian in, is really no surprise. It just reflects the fact that it is a gauge theory. Also, if we had have tried to calculate the propagator without that gauge-fixing Lagrangian term in, we would have been trying to invert a projection operator, which we couldn't have done. So the propagator wouldn't have existed. Now that we've added that gauge-fixing Lagrangian in and we've arrived at this result, it's no longer a projection operator, we could actually successfully invert it and get the propagator, but we're not going to do that here. Now we can make the gauge choice alpha equals 1. This is called the Feynman gauge, and the action simplifies down to that. We can integrate by parts one more time, ignoring the boundary terms for the same reason as previously, to get the form of the action that is usually used as the starting point for quantization in the Gupta-Bleuler formalism. The canonical conjugate fields simply work out to be this from that Lagrangian. We now see that there are no issues with imposing the usual equal time commutation relations, which are just these, and the reason is because that pi 0 is now no longer 0. The equations of motion, therefore, are simply this. So it sort of simulates the Lorentz gauge. These are exactly the equations of motion that are yielded by applying the Lorentz gauge to the gauge invariant field equations. This particular gauge fixing Lagrangian, followed by setting alpha equal to 1, therefore just simulates the Lorentz gauge at the equations of motion level. However, beyond the equations of motion, the two prescriptions are not the same. This more sophisticated Gupta-Bleuler prescription allows for quantization. If you just try and apply the Lorentz gauge condition directly to the free Maxwell Lagrangian, it won't do anything. However, if we simulate it with this Gupta-Bleuler prescription, we find that the Lagrangian does actually change, specifically in a way that causes pi 0 to no longer be 0, and therefore allows us to quantize. The major benefit of the Gupta-Bleuler prescription is that it allows for quantization without disrupting manifest Lorentz covariance. This, however, comes at a cost that the Coulomb gauge method does not include. In Gupta-Bleuler quantization, the Hilbert space ends up containing negative metric states, specifically the scalar polarization states are the ones that end up being negative metric states, and longitudinal states. Intuition and group theory tell us that these states, the longitudinal and the scalar ones, are unphysical. Additionally, the negative metric states, the scalar ones, are unphysical because their presence leads to the possibility of negative probabilities, so we lose unitarity. This is the ultimate effect of adding the gauge-fixing Lagrangian density instead of using the Coulomb gauge condition. The Coulomb gauge condition eliminates all of these undesirable states, whereas breaking the gauge with the gauge-fixing Lagrangian we're using here doesn't. It turns out that something similar to the Lorentz gauge condition can be used as a physical state condition that eliminates the unphysical portion of the Hilbert space and therefore restores unitarity. This is the last step in the Gupta-Bleuler program. Comparing this technique with using the Coulomb gauge, we see that it represents trading manifest unitarity for manifest Lorentz invariance. We will see this as we proceed. Just as a bit of a foreshadow, we'll show mathematically that it's the case that setting the expectation value of the divergence of the 4-vector potential equal to 0, but not just the straight-up divergence equal to 0, is exactly what's needed to eliminate the unphysical states. The key here being is that it's only true expectation value-wise, so we're not actually setting the divergence of the gauge field equal to 0, so therefore we're not actually destroying the quantizability that we got by adding that gauge-fixing Lagrangian on. That's what allows the physical state condition, which is alarmingly close to just the Lorentz gauge, to be maintained without reducing the Lagrangian back to the straight-up free space Maxwell Lagrangian and therefore destroying quantizability, which is exactly what would happen if it was true not just expectation value-wise, but if the divergence was actually equal to zero. The plane wave solutions to the equations of motion, which, if you've forgotten by now, are just these, take the following form and that of its complex conjugate, where k dot x equals k mu x mu. We see straight away that there are four linearly independent polarizations. Additionally, because we don't have the Coulomb gauge condition to eliminate the longitudinal and scalar polarizations, leaving behind the two transverse ones, as we did when we quantized in the Coulomb gauge, we must take into account all four of them, not just the two transverse ones. A subscript that can have four values will be added to the polarization vector to index this multiplicity. The usual parameterization for these polarization vectors is this, where the photon is taken to be traveling in the z direction. So we have the scalar polarization, these two are the transverse polarizations, and then this one is the longitudinal polarization. From this we find the following useful relations. It is worth stating that while the lambda index is not a space-time index, it is a useful formalism to take it to be raised and lowered by the Minkowski metric anywhere it appears. Also, the Einstein summation convention will be used for this type of index. Really all we're doing is defining the upper and lower indices to be related to each other by contraction with the Minkowski metric instead of just leaving it meaningless where you put the index. This is just an extra bit of definition. One can then write the general solution by constructing an arbitrary combination of the plane waves, of course, that transforms like a four vector. So we use this Lorentz invariant integration measure there, where the Fourier coefficients are Hermitian conjugates of each other to ensure that the field is real. One can also compute the conjugate fields using the formula computed above. That just gives us this result. We can now invert these relations to find formulas for the Fourier coefficients in terms of the fields. We can then commute them to arrive at the Fourier coefficient commutation relations. To invert, we must first find the value of these two integrals. I started by doing a slightly different integral, and then I'll contract it with the polarization tensor later. Plugging in the formula for the a mu and reworking the exponentials a little bit gives us this. We can now do this x integration using these integrals, which gets us here. Then we can use these delta functions to do the k integration, which gets us here. Then we can remember the formula for the contracted polarization tensors, and that gives us this and ultimately this result. Now that we're done, we can drop the primes and we have this formula. Now we can work on the second integral, so we start by doing this one, and again we'll contract the polarization tensor to this later to make it actually the integral we need the value of. Again, inserting the formula for the pi field and reworking the exponents. Then again we can use these formulas to do the x integration. Then we can do the k integration using these delta functions, which gets us here. Then we can contract with the polarization vector, and then remember the formula for the two polarization vectors contracted with each other, and then simply do the sum over the lambda index, and we get here. Then we can drop the primes again. That ultimately gives us these two values for the two integrals we needed, and we can do this combination of them to get a of k. So that's the first inverted relation we needed. And then we can take its Hermitian conjugate to get the other one we needed. Now we can start working out the commutation relations for the Fourier coefficients. Let's start with this one, the one we know will be non-trivial. So if we plug in the values in terms of the fields of those coefficients, and of course we have t equals t prime, then we can apply these commutation relations to simplify it down quite a bit. Some terms cancel, and the remaining ones can be written as commutators, specifically ones that can be evaluated with this relation. Then we can simplify by absorbing these deltas into the epsilons. That gets us here. Then we remember this relation. We can plug that in. Then we can sum the two like terms. Then we can do the x prime integration with this delta function. And then we can recognize the delta function that shows up as a result of this x integration, which gives us this final result here. The other Fourier coefficient commutators vanish trivially, so the complete set are as follows here. The Hamiltonian density and the Hamiltonian are as follows. We see the Hamiltonian density in this integral right here, and then the integral is equal to the Hamiltonian. So we can evaluate that and get this 1/2 times this thing as the result for the Hamiltonian density, and of course the integral over it is the Hamiltonian. We can now evaluate the fields we see showing up in here. They take on these values, and we can insert them to get this. Then we can remember this relation, which simplifies things down a little bit. Then we can multiply it all out and rework the exponentials. Then we can do the x integration to yield all these delta functions. Then we can do the k prime integration using those delta functions, and then we can simplify it, remembering this result here to this. Then using the standard normal ordering gives us the final desired result for the Hamiltonian. Now we can do a similar calculation for the momentum. We have this result for the momentum density, and the integral is just the momentum. We can insert the fields, then that gives us this. Of course, then we can multiply it out and rework the exponentials there, and the next thing we can do is we can recognize that these contracted polarization tensors just yield a metric. From here we can do the x integration, which gives all those delta functions again, and then we can do the k prime integration using those delta functions, which gives us this result. Then we can rewrite it in terms of two integrals strategically, because the first integral here has an integrand that is odd in k, so it vanishes, which leaves us this. The normal ordering ultimately gets us to this result. Now we can verify that the A daggers and A's do behave like creation and annihilation operators. Let's start with A of k. So if we postulate this arbitrary energy eigenstate, even though we haven't technically worked out how to build an explicit energy eigenstate, we can still postulate their existence and use them to study these operators. Then we can perform a calculation that should probably look very familiar to you if you're watching this video, but still I've written it out in complete detail. We can commute this operator through that one, and then we can do the commutator with this one, which of course yields that non-trivial non-zero value, which we can then simplify down. We can do the integral because of that delta function, and what we recognize is that we've got this A lambda applied to the Hamiltonian applied to the energy eigenstate minus this other term, which is just omega times that same annihilation operator applied to that energy eigenstate. So we can rewrite it like this and remember the property of these energy eigenstates under the Hamiltonian and factor it, and we get this result. So we can now drop those number indices on the lambda indices that differentiated them because the calculation is done. We see that they do in fact behave like lowering operators. Now we can do the same thing with the A daggers. The calculation is basically exactly the same, and again I've written it out here in full detail to make it easier for you, and they do behave like creation operators. So the A daggers behave like creation operators and the A's behave like annihilation operators. It is confirmed. Now, as usual, because the Hamiltonian is an integral over products like this, and the only such product that appears in the Hamiltonian with a minus sign is the one corresponding to the negative metric and therefore negative norm scalar polarization states, its expectation values are non-negative. So in order to understand what this means here, let's look back at the Hamiltonian for a moment. We see, given that we're in the mostly minuses metric signature, that the contributions from most of the polarizations, the three spatial ones, are positive. So therefore, the expectation values of those parts of the Hamiltonian are in fact positive, given that it's an A dagger times an A. It's this type of product that I just mentioned. However, we also notice that the scalar polarization contribution occurs with a minus sign. So that may make you think that the Hamiltonian couldn't possibly satisfy that condition. But what we'll show later on in this problem is that such states are negative norm states because they're negative metric states, which means that the minus sign will be compensated for by the negative norm nature of the states. So we get two minus signs, but they cancel against each other, so the expectation value of the Hamiltonian is in fact still positive or zero, even though at first it looks like there's a negative contribution to the Hamiltonian. Therefore, we can make the normal argument that there must be a lowest state that is annihilated by A of k, and therefore that one can construct all of the states by applying creation operators to the vacuum state. One-particle states can be written like this. Unsurprisingly, multi-particle states can be written like this. Notice that because the creation operators commute, the field quanta obey Bose-Einstein statistics and are therefore bosons. One can see from the energy and momentum operators that the total number operator is just this. As usual, it counts the number of field quanta in the state to which it is applied. We will make use of it later. The 0 point on the energy scale is set such that the energy of the vacuum has the value 0. As a consequence, we've got these two relations. With this done, there is only one thing left to do, and that is to address the above stated problem of there being unphysical states in the Hilbert space. I said that the Lorentz gauge condition would be the inspiration for a physical state condition that will exclude all of the unphysical states. Here is where we learn about that. First, we know from experimentation and theoretical group theory analysis that only field quanta with transverse polarizations are physical. The scalar and longitudinal polarizations are unphysical. We can also show that the scalar polarized field quanta are negative norm states, as I referenced above when I talked about the Hamiltonian. So let's now actually show that. Let's start by writing down a scalar polarized one-particle state with a finite spread in momentum space, which can be done by selecting this f function to have the suitable form. Now let's compute the norm. So we have this immediate formula for it. We can rewrite it in terms of the commutator, and then recognize that this term is going to vanish because it has an annihilation operator applied to the vacuum, which gives us this. Then we've got this value for that commutator, which ultimately gives us this. Then we can do the k prime integral and simplify, which gives us this. And because this is f mod squared, we know that this must be a negative norm state. It must be less than 0. So we've proved that key result for the scalar polarization. So the norm is in fact negative. Doing the same calculation for states with other polarizations reveals that they have positive norm because of the minuses in the metric. Remember, the metric here occurs with a minus sign on it. So it's only the time component of this relation that actually is negative. So the norm is in fact negative, as I said when I was talking about the Hamiltonian. Doing the same calculation for states with the other polarization reveals that they have positive norm because the minus signs in the metric right here compensate for that minus sign. We see that the cost of obtaining a covariant quantization of the electromagnetic field is not just the inclusion of polarizations that we know are unphysical. We also have negative norm ghost states. The Gupta-Bleuler technique is based on the fact that the following Lorentz gauge-inspired physical state condition not only eliminates the longitudinal polarization states, but that it also eliminates the negative norm scalar polarizations. So it's eliminating both unphysical polarizations, and because the negative norm states are due to one of them, it's eliminating all the negative norm states and restoring unitarity. Now, I talked about above that if the mathematics told us that we had to impose the divergence directly equals 0, then it would be an inherently inconsistent theory, because, of course, that would destroy that term in the Lagrangian that we needed to make the theory quantizable. So the fact that the theory tells us that it's actually true expectation value-wise and that the divergence isn't directly equal to 0 is the thing that allows this theory to not be inconsistent with itself, given that the expectation value here being 0 does not imply that the divergence itself is. This intuitively implies that, and it turns out that this is the condition that's actually easiest to work with. Let's show that this condition actually does exclude the unphysical states. Of course, we'll need to start with the formula for the A+ field. Now let's consider the physical part of the Fock space. We will start by not assuming that it contains no longitudinal or scalar states, and then apply the physical state condition to it, and then use that to show that the expectation value of the longitudinal plus scalar part of the number operator, all denoted N, L, and S, is always 0. This shows that these types of states are absent from the theory or have 0 norm, in which case they are innocuous because they obviously can't affect anything. So for the physical Fock space, we have that it's a tensor product between a transverse part and a longitudinal and scalar part, where you can see the notation that I've used here. We can write these generalized states like this. Personally, I think these are kind of pretty formulas. I don't know why. So now let's explore the physical state condition. We remember that it's this. If we then plug in this value of the A mu plus field here that we wrote down above, we find this value. Because of the K mu epsilon mu lambda factor, the transverse polarizations will simply vanish. Therefore, we have this. Because all the transverse operators vanish, this operator trivially annihilates psi t. Therefore, we have the following equation right there. Because this is true, we can then write this to finally show that the physical state condition really does exclude the scalar and longitudinal polarized states. We will use this equation to show that the expectation value of the longitudinal and scalar polarization number operator has 0 expectation value. From the general total number operator given above, we see that the number operator that counts the scalar and longitudinal polarized field quanta simply is this, and we can take its expectation value, which we see immediately written out, just gives us that. Now we recognize that the transverse polarized states are just going to pass straight through that, and we take them to be normalized to 1, which ultimately gives us this. Then we can use the physical state condition we got here to arrive at this relation, which we can then use to rewrite this value for the expectation value like this. Notice that the quantity in brackets acting to the left yields 0 because of this relation. And the reason why that is because these creation operators behave like annihilation operators when they act to the left. So we see that the physical state condition does in fact ensure that this expectation value is 0 as we needed it to. Because the completely general expectation value of n, L, and S is 0, we can see that the Gupta-Bleuler physical state condition does in fact eliminate the unphysical states from the theory, meaning longitudinal and scalar polarization states are absent or have 0 norm, in which case they're innocuous because they obviously can't affect anything. Therefore, our analysis is done. Okay, so now you have seen all the details associated with Gupta-Bleuler style quantizing the free electromagnetic field. You've seen how we use gauge fixing Lagrangians. You've seen the physical state condition. You've seen all the nuances of calculating the various operators and making the needed arguments to construct all of the states of the theory. You've seen how, in fact, a simple but critically different than the Lorentz gauge physical state condition does eliminate the non-physical states from the theory. The only longitudinal and scalar ones that can possibly be left are 0 norm and therefore don't affect anything. So it yields an equivalent theory. It yields proper free field quantized electromagnetism. It does it in a bit more complicated form, but a manifestly Lorentz covariant one. And in the end, when you apply the physical state condition, it does yield a properly unitary theory with no unphysical states in it. I hope this video helped you understand quantum field theory better, especially this really key part of quantum field theory. I hope it helped you love quantum field theory more. I hope it was entertaining and fun and instructive. If it did help you, please give it a thumbs up and don't forget to subscribe. Dietrich out.